Okay, so today we are starting to solve chemistry AS level 9701 June 16 variant 23. uh, we will be solving all the variants, but before that let me tell you something, that I will not solve all the questions, only those questions that appear to be difficult or needs a lot of explanations. I will be going for the solve of only those questions. Okay, so let's start. So question number 1, an experiment was carried out to determine the percentage of iron in a sample of iron ware. Okay, so that is the thing. Okay, so 3.35 gram piece of ware was reacted with dilute sulfuric acid in the absence of air, so that all iron atoms are converted to iron 2 ions. This is a key point. So all the iron is converted to iron 2 plus. The resulting solution was made up to 250 cm cube. Okay, this is the important point. The resulting solution is made up to 250 cm cube. That is, the solution is being diluted. Okay, so what's going on? That okay, let's go for solving. I hope you can see. Let me rearrange it. Okay, so iron is reacting with what? Iron is reacting with sulfuric acid to form iron 2. So it will be iron 2 sulfate. It's FeSO4 plus hydrogen gas. If you don't remember, then let me tell you that metal react with acids to form salt and hydrogen gas, and sulfate has a valency of 2. So sulfate and iron, they have the same valency, so they are just present in the ratio 1:1. Okay, so what happens is that, so iron reacts with sulfuric acid to give iron sulfate. So the solution that remains is the iron sulfate solution. Okay, now let me go back to the question. Dilute sulfuric acid in the presence of air, so that all the iron atoms were converted to iron 2 plus. Okay, so there is no indication of sulfuric acid, that what has happened to it, but iron sulfate is that all iron is converted to iron 2 sulfate. Okay, okay, so then iron 2 sulfate, to which water is added. That means this is the dilution step, and after addition of water we are getting a 250 cm cube solution of iron 2 plus or iron 2 sulfate. So this is the raw solution, that means we are getting just after the reaction, and this is the diluted solution. Okay, so now what was the question? Let's go back to the question again. The question was okay, write a balanced equation. Already done. A 25 cm cube of this solution was acidified. Okay, which solution? The 250 cm cube solution is made, and then 25 cm cube is withdrawn from this solution. Okay, now let me tell you that what will be your thinking here. So when you are diluting a solution like this raw iron 2 sulfate, and this is the diluted iron 2 sulfate, all right. So when you are diluting this, when you are diluting a solution, the number of mole remains the same in the raw solution and the diluted solution. Okay, that means the now sorry. Okay, So when you are diluting a solution, the number of moles in the raw solution and the number of moles of substance in the diluted solution, it remains the same. Like talk about iron. So iron in this raw solution and the number of moles of iron in this diluted solution will be all the same. But now just remember that you are just withdrawing some solution from here. Just imagine like that, that after you have prepared the solution, you are just taking out 25 cm cube from this solution. That means you are taking out some of the substance, isn't it? That means you are taking out some of the moles from this solution. Okay, so think it in that way. So this solution and the solution you are taking out is from the same container, isn't it? So they have the same. Oh, I'm so sorry. It was a phone call from one of my student. Okay, so let's get back to studies. So where were we? We were just doing some reactions. Okay, so this 25 cm cube solution is withdrawn from the same solution, I mean from this solution, isn't it? So this one and this one, they must have the same concentration, but the mole number would vary. All right. Okay, so now what was the question later? Okay, let's see. So then the 25 cm cube of the solution was withdrawn and was acidified. That means hydrogen ions were added and titrated with 0.250 mole per dm cube potassium dichromate. Okay, so this solution, this 25 cm cube iron 2 plus solution is reacted with okay, so the 25 cm cube solution that contains iron 2 plus was reacted with potassium dichromate, and here we need 32 cm cube of potassium dichromate. Okay, so we have got the volumes. Do we know the concentrations? Yes, we do. We know the concentration of potassium dichromate. Look above. So concentration of potassium dichromate is 0.025 mole per dm cube. Okay, and two reactions are given, and we need to add up the two reactions to give an overall reaction. Okay, let's go. Okay, so it's 0.025 mole per dm cube, this solution. Okay, so the two reactions are Cr2O7 2 minus plus 14H plus 6E minus. This gives 2Cr3 plus and 7H2O. 6, isn't it? So 6. Okay, all right. And another equation is Fe2 plus, this will give Fe3 plus electron minus. So these are the two half equations. Why they are called half equations, let me tell you. Because our redox reaction consists of two parts. One is the part which is being oxidized, and another is the part which is being reduced. Okay, so when there is an when there is a part of oxidation and there is a part of reduction, if the oxidation and the reduction parts are combined together, we call it a full equation. But look at this equation. This equation shows only reduction. Why? Because it shows a gain of electron. Look, electrons are present in the reactant side, but electrons are absent in the product side. So presence of electrons, absence of electrons, which means the reactants must have absorbed the electrons and from the products. So this reaction only shows reduction. But what about this one? Look, in this side the electrons are absent, in this side the electrons are present. So from reactant to product side, electrons are emitted or electrons are released, and release of electron we call it oxidation. So this reaction shows only oxidation. So this reaction shows only reduction and this reaction shows only oxidation. That means both these equations are half of a redox reaction. Read the first half and ox the second half. Okay, so that's why these are called the half equations, because they are showing only they are expressing only the oxidation or reduction, not the full part. Okay. So now when you are asked to write the full equation, then you must first balance the number of electrons. So here is 6 electrons, but here is 1 electron, so multiply 6 here. If 6 is multiplied here, then 6 is multiplied here, then 6 is multiplied here. Then what you need to do is just add up the reactants and the products and cancel out the electrons. But before doing this, you must make sure that electrons are in opposite side of the two equations. Like here electrons are in the reactant side and here the electrons are in the product side. Before doing this, you must make sure that electrons are in the opposite side of equations. If not, then you make some internal conversions. Okay, so it will be like Cr2O72 minus plus 14H plus 6 Fe2 plus. This will give 2 Cr3 plus 6 Fe3 plus 7 H2O. Okay, so this is the overall equation. Okay, so calculate the amount in moles of potassium dichromate used in the titration. Okay, so you know that concentration is given, volume is given, so just calculate the moles. 0.025. okay, the formula is concentration into volume divided by 1000, isn't it? So we are applying that formula, that concentration into volume divided by 1000. Hope you can see it. So concentration into volume, we need to divide this by 1000 because this is given in cm cube, so we are converting it into dm cube, and the answer would be 8 into 10 to the power minus 4 moles of potassium dichromate, or simply dichromate. Okay, so what is our next question? Amount in moles of iron in 3.35 gram piece of ware. 3.35 gram. Okay, now here is an important concern. Look, what? Okay, look, so this iron has a mass of 3.35 gram. All right, okay, so this iron, or this amount of iron, the iron present in 3.35 gram is reacted with sulfuric acid to form iron 2 sulfate, which is then diluted. That means the number of moles of iron present here is same as the number of moles of iron present here, and since this solution is simply the diluted version of this, so number of moles of iron present here is also equal to number of moles of iron present here. So these three are linked, and we are doing the titration from this solution. Okay, so we are doing titration from this solution. Okay, so let's find that what is the number of moles of iron present here. Okay, so look, So 1 mole, is it finished? 1 mole of dichromate reacts with 6 moles of Fe2 plus. So if this is the number of moles of dichromate, so number of moles of iron would be 8 into 10 to the power minus 4 into 6. That means 4.8 into 10 to the power minus 3 is the number of moles of Fe2 plus present in the 25 cm cube solution, because we are doing we have done the titration, the dichromate titration with the 25 cm cube sample, isn't it? Okay. Okay. So, oh, the working is not finished yet. Okay, so this is the number of moles of iron present here in the 25 cm cube sample. I need a pen. Okay. So in this sample, in this 25 cm cube sample, we have 4.8 into 10 to the power minus 3 moles of Fe2 plus. This is 25 cm cube and this is 250. Okay, so let's carry out the calculation. So 4.8 into 10 to the power minus 3 moles of iron 2 is present in 25 cm cube. So how many moles are present in 250 cm cube? It's very simple. So it's just a 10 times. So x will be equal to 4.8 into 10 to the power 4.8 into 10 to the power minus 2 moles of Fe2 plus. So this solution contains 4.8 into 10 to the power minus 2 moles of Fe2 plus. Okay, so that means here we also have 4.8 into 10 to the power minus 2 moles of Fe2 plus. So here also 4.8 into 10 to the power minus 2 moles of Fe2 plus are present. Okay, so while you are doing this kind of mole calculation, you must be careful to read, to first read that what are the hints given, what are the ways of calculations given, what are the procedures of experiment that has been followed in that case. You must read very carefully and then go through the calculation. Okay, so here 4.8 into 10 to the power minus 2 moles of iron 2 plus is present. Okay. So the question asked, okay, moles found, moles 4 done, now 5. 5 is also done, so number 6, the mass of iron. Okay, so what we have the number of moles of iron, which is 4.8 into 10 to the power minus 2 moles, and to find the mass we know that number of mole equals to mass divided by the atomic mass or molecular mass. So mass will be equal to number of moles into RMM or RAM. So it's 4.8 into 10 to the power minus 2 into the atomic mass of iron is 55.8, which will be 2.678 grams. Okay, so that 3.35 gram sample of that iron contains actually 2.678 gram of iron. Okay, so what was the next question? Okay, so the percentage of iron the percentage of iron in the 3.35 gram. Okay, so the percentage would be 2.678 divided by 3.35 into 100%, which is almost 80%. Okay. Okay, So what was the next question? Okay, some electronegativity values are shown. Use the data to suggest the nature and bonding between iron, nature of the bonding in iron 3 chloride. Explain your answer. Now you know that while we were studying bonding, I told you that if the electronegativity difference is between 0 to 1.9, then the type of bonding between the atoms will be covalent, and if the bonding is greater than 2, then it would be ionic bonding. Okay, so look at the difference between iron, and chlorine. So iron has the electronegativity of 1.8, and chlorine has the electronegativity of 3. So the difference between them is 1.2, which is much less than 2. So the bonding between iron and chlorine, it must be covalent. So you would say that the difference is much less than 2 or is smaller than 2. So the bonding between iron and chlorine has to be covalent. Okay, and you must also remember that covalent oxides or covalent chlorides, except CO and H2O, are all acidic in nature. All covalent compounds, with the exception of few like H2O and CO, they are all acidic in nature. So iron 3 chloride, FeCl3 in this case, would also be acidic. Okay, now here is a important fact to learn. Okay, now when a metallic chloride is acidic in nature, then it dissolves in water to produce some compounds where or to give a reaction where there is the coordinate bonding between water and the metal ion. Look, I'm giving you the example of aluminium. Aluminium chloride, it is also acidic. So when it dissolves in water, what happens is that aluminium becomes, it's 3 plus, all right. So aluminium becomes surrounded by 6 water molecules. The lone pair of the the lone pair of oxygen atoms on the water molecules are donated on aluminium. So this is what happens. Electron pairs here, H2O, electron pairs here, H2O, electron pairs here, H2O. Okay, so this is what happens when metal actually, instead of dissolving, it also reacts with water. This is what happens. Okay, so the thing is that especially the transition metals, they also react in the same way. Okay, so what will happen is that it will be Al H2O6 3 plus, because water is neutral and aluminium has got a charge of 3 plus, and we will get 3Cl minus. Okay, so just you just need to memorize the reaction, that when any metallic chloride which is covalent dissolves in water, it carries out this type of reaction, and this 6 water molecule is a fixed number for all the metals. Okay, so when FeCl3 dissolves in water, it reacts in the same way. it produces FeH2O6 2 plus and 3Cl minus and 3Cl minus. and now if and now what further happens is that this AlH2O6 or FeH2O6, they carry out a further reaction. Shall I zoom it? They carry out a further reaction to give or to release H plus ions in water. Look, AlH2O6 3 plus, okay, this gives AlH2O5, and one water molecule breaks down into H plus and OH minus, and the OH minus remains here. So 1 minus and 3 plus now gives 2 plus, and 1 H plus is released. Same goes for iron. FeH2O6 3 plus, this will FeH2O5 OH 2 plus and H plus. So you can write this one as your answer, or you can write this one and this one as your answer. It's totally your wish. But remember that here water molecules are forming coordinate bonds or coordinate covalent bonds or dative covalent bonds with the metal ions. Okay, now let's go to the next question. Ammonium nitrate is an important fertilizer by an acid-base reaction. Okay, write an equation for the production of ammonium nitrate from ammonia and nitric acid. Ammonium nitrate, you know that ammonia plus nitric acid, this will give ammonium nitrate. Still, I'm showing the reaction. So ammonia plus HNO3, here nitrogen has a lone pair of electron, it will accept the hydrogen ion from here, so it's a bronzosylate base, it's a bronzosylate acid, it produces NH4 and NO3. Okay, the ammonia for this reaction is produced by the Haber process, and the nitric acid is produced by oxidation of ammonia. The Haber process involves the reaction between nitrogen and hydrogen at a temperature of dash 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 dash. At a higher reaction temperature, the rate of production of ammonia would be greater. What? Okay, the rate of production of ammonia would be greater. Let me tell you something. Don't ever confuse between the equilibrium and the rate. They are not from the same perspective. Rate of reaction is due to the movement of the molecules or the kinetic energy of the molecules, and equilibrium is about the yield or the amount of reactants and products, the relative amount of the reactants and products, and rate is all about just that how much they're present and what will be the extent of collision between them. Okay, it has nothing to do with the amount of products or the amount of reactants present. Okay, so here we are talking about rate. Okay, so the rate at higher temperature, the rate of reaction would increase, but that doesn't mean the yield would increase, because yield depends on the position of equilibrium. Rate and equilibrium, I'm telling again, rate and equilibrium do not merge the concepts. A higher rate of reaction no way means higher yield. Yield only depends on equilibrium. Okay. Okay. So a Boltzmann distribution curve shows the distribution of energies in a mixture of nitrogen and hydrogen at 450 degrees Celsius. So sketch a second line onto the axis to show the distribution of energies in the same mixture of gases at a higher temperature. Okay, so the temperature is higher. So the temperature is higher. Okay, so this is the activation energy line. So if the temperature is higher, then there must be so these are now the reactive molecules, and we are calling it as a reactive region, and this is the unreactive region. And now if the temperature is higher, then there will be more reactive molecules, so the area of reactive molecules increases, and the area of unreactive molecules decreases, and the peak also goes down. So the curve shifts like this. Okay, look, the area of the unreactive molecule region has decreased, and area of the reactive molecule area has increased. Okay, now what was the next question? With reference to your curve, explain why the rate of production of ammonia would be greater. Rate of production of ammonia would be greater at higher temperature. I mean, this is a very common question. You have been dealing with this question from all since class 8 or 9 or O levels. So let's make the answer simple. Okay, so yeah, just look at the curve with reference to the curve, since it said. So there are now the number of molecules with energy greater than activation energy. This is the activation energy, so number of molecules with energy greater than activation energy is now greater. So there are now more successful collision, more number of collision, more energetic collision, so the rate of reaction would be greater. Okay, now what? Add a suitable label to the horizontal axis above it to explain why a catalyst is used in Haber process. Okay, so what happens? This is very important. So what happens is that, suppose this is the curve, this is the line of activation energy. So when you are adding a catalyst, the shape of the curve does not change. Instead, activation energy decreases. That means it shifts backward. Okay, so for example, activation energy line is here. So initially this was the region containing reactive molecules, but now this is the region which contains the reactive molecules. All right. Okay, so we would say that activation energy shift to the left, so the region containing reactive molecules who have energy greater than activation energy would increase, so the rate of reaction would for sure increase. Okay, explain why a higher temperature is not used despite the fact that it would increase the rate of production of ammonia. Now, okay, remember, let's go back to that last page. Look here, look at the reaction between nitrogen, hydrogen and ammonia, which gives an enthalpy change of minus 92. just remember that when enthalpy change is given for a reversible reaction, then a reversible reaction has two sides, from left to right and from right to left. Unless stated, the enthalpy change given will always be for the left to the right side, and here in this case the enthalpy change is minus 92. Okay, minus 92. So Minus 92 means the reaction from left to right is exothermic. Left to right is exo, and from right to left will be endo. Now you remember the short form hen. So at high temperature, endothermic reaction is favored always. So if you increase the temperature, or if you are using a high temperature, then what happens is that nitrogen plus 3 hydrogen, this will give 2 molecules of ammonia. This is exo, this is endo. So high temperature favors endo, so the reaction will be endo at high temperature. That means more ammonia is broken down to give nitrogen and hydrogen. That would be the problem. So that's why we are not using high temperature. Okay, rest of the questions like question C, question D, question E, you must all memorize all these questions. There are no other ways. Especially question D1 is very important. The drawing of ammonia and the number of bonds present in NH4Cl or ammonium compounds like NH4NO3, or which type of bonds are present, etc. The question appears frequently in CAIE-AS papers. So these questions are very important. We must get to know that ammonia has got normal covalent bond, the dative covalent bond, and ammonium compounds has got the normal covalent bond, the dative covalent bond, and also the ionic bonds. Just remember. Okay, so that's question number 2. Now we are shifting to question number 3.